In this course, we are going to study battery management systems, or BMS. These have to do with properly managing or controlling, in some sense, battery packs. And we really have in mind large battery packs having many cells, although any battery pack having more than one cell, or even one cell, I suppose, could benefit from the topics that we discuss. The picture on the right shows some components of a battery management system that was manufactured by a local company in the Colorado Springs area some years ago. And so you get an idea of what a battery management system looks like. It might have one or more electronics boards with components on them and processing on them and so forth that we would put inside of some enclosure to keep it safe from the elements, and then we would have these connectors that communicate between the battery management system and the battery pack and the vehicle controller and so forth. This was a vehicular application. So that's what a battery management system looks like. It's an electronics board. It's kind of like a computer board with specialized parts on it to be able to perform the functions that we'll talk about in this chapter and we'll introduce in this lecture segment, actually. So a battery management system is what is known as an embedded system, and my definition of an embedded system is purpose-built electronics plus processing to enable some specific application. So this is not a general purpose computer like a PC or a Macintosh or anything like that. This is special purpose-built electronics that has components on there that are tailored specifically to the job of managing or controlling a battery pack. And then there's processing on there also, some kind of a microprocessor or a microcontroller or perhaps even an FPGA that implements certain procedures or algorithms to actually do the control or the management of the battery pack. There are several goals that must be accomplished, met by the battery management system, and I've tried to rank them in some kind of order, although they're really all important. So one of them is to protect the safety of the human being who is living in proximity to the battery pack. So if there's anything unsafe happening in the battery pack that could potentially cause maybe a fire or maybe some short circuit that or some electrical connection that's not properly insulated or isolated that could pose a shock hazard to the operator. Anything like that is the foremost requirement of a battery management system, is to keep the user safe at all times, no matter what. And if a battery pack, for some uncontrollable reason, has entered an unsafe condition, to at minimum notify the operator that something bad has happened and to get away from the situation. So I've heard of one electric vehicle manufacturer having some kind of notification on the dashboard that said the battery pack is compromised, please pull over to the side of the road and get out, and I've heard of that working successfully. So it's not ideal. You don't want the battery pack to fail. And sometimes, though, if you're in an accident or something, there are circumstances way beyond your control that do cause a failure, and we should at least notify the operator of what the hazard possibilities are. So number one, keep the operator safe. Number two, keep the battery safe. The battery is a very expensive investment, and even in a hybrid vehicle, and we'll talk about some of the vehicle classifications on the next page, I think. But even a small battery pack for a hybrid electric vehicle is the most expensive single component of the drivetrain. So it's a huge objective to keep the battery safe from damage in two kinds of cases. One, if there's some kind of an abuse failure case, we would try to minimize the damage that happens. So that is things outside of our control, basically, is to try as much as possible to protect the battery pack, but also in normal operating situations to protect the life of the battery pack by not allowing, for example, over voltage or under voltage type of operation, as just two examples of that. So safety of the operator, safety of the battery pack, and then finally we get, those are kind of binary things, but then we get down to things that are a little bit less binary, which have to do with trade-offs and optimizations, which, for example, maintain the battery in a state in which it can fulfill its functional design requirements. And that probably doesn't make a lot of sense, but just as an example, remember, state of charge indicates, roughly speaking, if the battery is full or empty or where it is in between. And we'll talk more about what we mean by state of charge in the context of a battery pack, but at least on a cell level, it says state of charge of 100% is a fully charged cell, state of charge of 0% is a completely empty cell, and somewhere in between is somewhere in between. Well, if a cell is fully charged, it cannot be charged any further, which is an obvious statement, but that means that an electric vehicle battery pack may not ever be fully charged in the sense that we think about it in 5710, because that would not allow the battery cell to accept energy from the regeneration process of braking. So when I hit the brakes on an electric vehicle, it does use friction brakes, but it also captures some of the energy and puts it into the battery pack, which is one of the reasons that we can get better efficiency with hybrid vehicles than we can with just pure combustion vehicles. So a cell state of charge of 100% might not be within the design window of a vehicle application. We might have to derate that to say that the maximum charge in the vehicle might be something like 95% to allow us to be able to accept this regeneration. And similarly, a cell state of charge of 0% is something that we would never want to happen in a vehicle because, yes, we've got all the energy out, but at the very, very low energy, the low state of charge area, I can't get any power out, because if I try to pull power out, it would result in an under voltage situation. So as a very minimal example, we might want to maintain a state of charge design range, just say 10% to 90%. This is, the design range is a design variable. You have to decide what that range should be when you're making an application, but once you have a requirement on the application that says the cells must always be between 10% and 90%, that's the job of the battery management system to make sure that happens. And how it happens is in a very passive way, usually. The battery management system has very little ability to influence its own state. It is an advisor. It advises the vehicle controller or the application controller of how much energy is available or how much power is available for the application to use. The battery management system doesn't use the power, but it tells the application how much power or energy can be used. And if the application obeys the advice, then the battery management system is actually maintaining the proper state. If for some reason the application does not respect the advice that we give it, then in some cases, in extreme cases, we would protect ourselves from the application by shutting down, by opening a contactor, which is a fancy name for a big relay, to disconnect the battery pack from the load to prevent damage because of this abuse that is being imposed by the application itself. This is a very, very tricky problem, and it's application dependent of when does the battery management system step in and take the battery offline, or what kind of prerogative does the battery management system have versus the application, and that's going to be different for any kind of application. For example, we may tell the application, you have very little energy or power available right now because we're very near our design limit, but the application may decide, uh-oh, Grandma just stalled the car on the railroad tracks, so even if I damage the battery pack, I've got to drive off the railroad tracks at least, so I'm going to get at least a little bit more energy out. I might slightly over-discharge the battery pack, but that's a better situation than having an accident. So very, very tricky kind of philosophical questions. But once we have a design specification, which come out of those philosophical kind of thoughts, once we have a design specification, then the battery management system is designed to achieve that specification. The battery management system is sometimes a fairly expensive piece of hardware. It can be hundreds of dollars. Now, compared to the price of a car, that might not seem like very much, but automakers really try to trim the margins so that they have the best price that they can have. They're very low margin market compared to some others. So the cost associated with battery management is something that they consider very carefully. So if you say, well, I can improve battery management if I put this new algorithm in, but that requires spending $50 more on a processor, you're going to have to show them how they can save more than $50 somewhere else before they will even consider listening to you. So cost is critical. Now, cost is also relative. And when we're talking about batteries for any application, your battery is considered, this is a rule of thumb, to be cheap enough if you can't remember the last time you replaced it. So if you replace a cell phone battery and it costs you, I don't know, a few tens of dollars to replace, you'll remember that for a few weeks as, ouch, I couldn't go out to eat for a month because I had to buy this battery for my cell phone. I'm not really happy about that. But after maybe a year, you've kind of forgotten exactly when you replaced it, and the pain has gone away. So that's a few tens of dollars. But for a hybrid electric vehicle or an electric vehicle, the battery pack is significantly more expensive. It's in the thousands of dollars, and you're going to remember for a very long time if you had to replace it. Now, they're designed so that you never have to replace them on a vehicle. They're designed to last 10 years minimum. They usually warranty them for at least 8. But with proper care and feeding, they should last longer than that, probably 15 years. But if you ever do have to replace your battery pack, you're going to remember that forever, and it won't have been cheap enough. So there's a trade-off between the upfront cost of battery management and the later cost of having to replace a battery pack if the battery management failed because it wasn't designed with the best possible methods, because you wanted to cut costs. So there's a trade-off between what you invest in the battery management system and what you gain from that. And that's something that's always considered, especially in automotive applications, in my experience. So larger battery packs have a much greater investment, and they motivate much better battery management, which allows us to use some of the advanced tools that we talk about in this course. Small battery, like a cell phone battery, may not be a large enough cost of the battery itself to really make sense for us to use the most advanced methods in this course, although we also talk about some simpler methods that may be used instead. But we're looking at the best methods that I know of for equivalent circuit type cell models applied to battery management. And those methods, these best methods, are supported by large battery packs, for example, vehicular applications, although the methods we discuss will work for any kind of battery pack, including things like grid storage and frequency regulation and whatnot. So by now you probably know very well that most of our research here at UCCS on battery systems is motivated by a vehicle application. We have been privileged to work with a number of OEMs over time. And these vehicle applications are kind of very broad when you think of the type of vehicle that the battery pack is put in, and they're given different names, and I'll review these names here. So hybrid electric vehicle and plug-in hybrid electric vehicle and extended range electric vehicle and electric vehicle or battery electric vehicle, and even sometimes a mild hybrid or a start-stop hybrid. So there's different vehicle classes, and the biggest difference, there's a lot of differences, but one of the biggest differences is how big a battery am I putting in the vehicle. So a start-stop hybrid or a mild hybrid electric vehicle has a gasoline engine, but it also has a small electric motor. It's really just a starter motor that's kind of beefed up for more regular operation than a traditional starter. And the start-stop hybrid stops the engine when you're paused at a red light, and it starts it up again afterwards. So it has very little energy storage. It just really has enough to start and stop the engine a lot more frequently than your regular 12-volt lead-acid battery does. A hybrid electric vehicle, as opposed to this mild hybrid I just discussed, has a somewhat bigger battery pack that's able to do more than simply start the engine frequently. It also fills in some extra power demand when the gasoline engine is not able to keep up. So because I have a gasoline engine or some other source, usually a gasoline engine, and the electric motor, the gasoline engine can be designed a little bit smaller than for a comparative size vehicle, because we're going to take the average energy, or average power rather, out of the gasoline engine, and we're going to take the peak power, the peaks around that average, out of the battery, and use the electric motor to fill that in. And we'll also use braking and deceleration events to use that recovered energy and put that back into the battery pack in order to gain efficiencies that way. So we have efficiencies gained because we have smaller engines, and gasoline engines that is, and we can recover some of the energy from braking and from coasting. These hybrid electric vehicles have essentially zero electric range. The range depends entirely on gasoline, but we use the battery to kind of fill in the power. So the Toyota Prius, which is right here, was one of the first hybrid electric vehicles on the market. The Honda Insight was another one, and there was another one whose name I forget right now that was around the same time, but they were very early electrified vehicles, and they were hybrid electric vehicles. Nowadays, hybrid electric vehicles can have some all-electric range, but it's usually fairly short. So I can run all-electric up to maybe 20 miles an hour for a short period of time, which helps with stop-start traffic and things like that, like downtown Los Angeles in rush hour. The next size up that's given a distinct name is a plug-in hybrid electric vehicle. And this has a larger battery than hybrid electric vehicle, and the difference is the hybrid electric vehicle you never plug in. The energy in the battery arrives there because of the gasoline engine and the alternator and so forth that puts energy back into the battery pack. But a plug-in hybrid you could plug in at night or whenever, and so you can get energy off the grid to charge your battery pack. So we have a somewhat larger battery, and this allows some all-electric range under certain operating conditions. And the electric range is usually between 10 and 20 or so miles for a plug-in hybrid, and it's usually under a fairly low speed, less than highway speed. The next step up is extended range electric vehicle, which is again a plug-in type vehicle. Both of these can get some energy from the gasoline engine, but they're not really designed to do that, not to recharge all the way. So I get some range from plugging it in, and it's a larger range. And this range is available under full load conditions rather than under certain operating conditions. So I can be driving generally highway speeds and so forth, all electric, with some caveats with the extended range electric vehicle versus the plug-in hybrid electric vehicle. So you can see there's kind of gray areas. These are not distinct, crisp categories. You might even say that they're marketing terms that the companies have come up with to distinguish their product from some competitor's product, but they represent overall a whole spectrum of possible electrification. So the Chevy Volt is the first extended range electric vehicle on the market. Oh, by the way, the Prius also is available in the plug-in version at this point in time. I don't remember what the range is, but it's between 10 and 20 miles. The Chevy Volt has a range of nearly 40 miles in its first iteration, and I understand that they will be announcing this month the next iteration, and we're looking forward to seeing what the specs are on that. And then the final extreme is a pure electric vehicle, where the only source of motive power comes from the battery. So you have to plug this in at some point in time, and the battery allows you to drive for a period of time. That is a Nissan Leaf. Some other examples, there's a Ford Focus electric, and there's also, of course, the Tesla Roadster and Tesla Model S are the very high-end, extremely wonderful vehicles from everything that I've heard. So I know people who have leased Leafs and they love them. I know people who they've driven the Ford Focus. They thought that was great. Student has a Tesla. He can't say enough good things about it. Another student has a Chevy Volt. Another student has a Prius. So I don't have any of these. I'm the biggest hypocrite out there. I don't own an electrified vehicle yet. I'm waiting, but I look forward to when I do have one. But really everything that I've heard is extremely positive. These car makers took very big risks to be able to bring these vehicles to market because they're so different in many ways from everything that they know how to do, all the gasoline engine stuff. They know that. They've done that for 100 years. But the electrified is pretty new, so there was a big risk to bring them to market. And because they knew there was that risk, they designed them really well. These are well-designed, rock-solid vehicles, is my understanding. So again, that's not a personal testimony, but that's what I've observed and I've been told. So those are applications of vehicles, and what is important about them is that they have battery packs that are large in some sense, they're high voltage in some sense, and they're high current in some sense. These are different from your portable electronics that typically have maybe one or two cells, and they're not especially large. They're low voltage and relatively low current. Among the different vehicle applications, there are distinctions in how we would design different battery packs, and we'll talk about that when we need to. But overall, the commonalities tend to be more significant than the differences, and I will use a generic term when the distinctions aren't important. So you saw that everything ended with EV. I've got HEV and PHEV and EREV and so forth. So we'll just call it XEV, where X stands for any of the above. And as I already noted, there are other large-scale applications like grid storage and backup. So suppose the electric utility grid goes down in some area, we can have a big battery pack on a semi that drives in and powers, for emergency purposes, a neighborhood or a subdivision for a period of time until we can get the electric grid back up. That's one possibility. It's already been done. Frequency regulation is related but different application where it's kind of like a hybrid system where we still use regular type of ways of generating electricity for the grid, such as, coal, gas, wind, solar, all these things that power the grid right now. But when the grid experiences a power transient of, all of a sudden some really big power demand came up, what that does is it puts a huge load on the grid, and it and the frequency goes down. All of the spinning reserves of the generators slow down, and so the frequency goes down, and that's bad because they have to maintain a constant 60 hertz. So people are building now battery systems that whenever there's a large load demand placed on the grid, the battery system kicks in and supplies not the entire demand, but just the difference between the expected demand and the required demand, so that we can keep the frequencies regulated properly. And then when there's less demand than expected, those battery systems then recharge their battery packs. So they're kind of the same way a hybrid electric vehicle has a gas engine and the electric motor, and the electric motor fills in the peak demand. The frequency regulation has the regular generation, but also this battery reserve that can fill in the peak demand also. Battery packs that we're talking about are high power battery packs, and we know from basic circuits power equals current times voltage. So for power to be big, I either have to have high voltage, or I have to have high current, or I have to have both. Well, we've seen battery cells, and by now you understand battery cells quite well. And we know that battery cells really can't have voltage, at least we don't know how to make battery cells right now with voltage above around 5 volts. And most lithium-ion cells have peak voltage around 4.1 or 4.2 volts. So in order to get high voltage, I can't do it from an individual cell, but I can do it by placing a lot of cells in series. So if I place cells in series, Kirchhoff's voltage law says that the voltages add, and so the pack voltage, if all the cell voltages are the same, is just the number of cells in series, ns, times the voltage of any particular cell. Of course, the individual cells may have slightly different voltages, so a more general way of writing that would be the sum of V cell I for I equals 1 to ns. That would be a little bit more precise. Cell construction places limits on how much current a cell can produce or sink. So you wouldn't want to take something the size of a watch battery and put a few thousand amperes of current through it. That would just melt. So for very high current packs, I have to wire cells in parallel. And when I wire cells in parallel, the overall current is divided between the different cells, so each cell experiences a different current, and if everything is equal, every cell experiences 1/nth of the total current. And so if I have a design limit on how much cell current can be, then the pack current can be NP times that, where NP is the number of cells in parallel. And again, maybe it would be a bit more precise if I said that the pack current is the sum of the cell currents, but at least back of the envelope thinking for design, we can think of the pack current being NP times cell current. So I can achieve high power either through high voltage or through high current. There needs to be some additional criteria that tells me which one of these I want to emphasize, because usually we actually emphasize both. We put some cells in parallel and some in series. Not always, but usually. And so how would I know to achieve a certain power how many cells to put in parallel and how many in series? Well, that's an interesting design, and it's usually determined by economic and safety factors. We usually, even if I have a series pack with 100 or more cells in series, we usually break that up into modules where the total voltage of the module is less than 50 volts, and that's for safety concerns. It's relatively difficult to kill yourself with 50 volts or less, and it becomes progressively easier to kill yourself with voltages above 50 volts. And so someone has decided that 50 volts is the threshold for safety, and we then try to keep things under that. So that's for individual modules. So if a technician or someone is going in and mistakenly touching both sides of the module and gets 50 volts across their two hands, they'll probably be safe. But we need to get more than 50 volts in the application, so we actually do wire modules in series, and the overall pack voltage is usually kept less than 600 volts, though. because when I approach 600 volts, some of the power electronics, the insulated gate bipolar junction transistors, for example, become very expensive and very difficult to design at voltages higher than that. So we try to keep it below. So for some examples, a lot of vehicle battery packs are around 300 volts. And Toyota has a really clever scheme where they've got a 250 volt battery that they internally double the voltage up to 500 volts using power electronics. But the battery pack itself is 250. So you can see that we're leaning towards high voltage rather than high current. Well, why is that? Well, because the power losses in the wiring are proportional to current squared. So if R is the resistance of the wiring inside of your vehicle, then the power lost heating that wire, the IR drop over that wire, is I squared R. So if I is big, I squared is much bigger. If I is small, I squared is relatively smaller. And this allows us to use smaller diameter wires. Well, smaller diameter wires have higher resistance than big diameter wires. So why would we use them? Well, because they're cheaper. A big diameter wire requires a lot of copper usually, and copper is expensive. So power electronics can be less expensive than copper. And so there's a trade-off here between the voltage that I use, because that's going to drive the cost of power electronics, and the wire diameter that I use, because that's going to drive the price of copper. Again, it's a great big design trade-off. So someone has to figure out what that trade-off should be, and then we get a specification from that on our battery pack, and that allows us to design what the voltages are and the currents are. So that tells us how many cells I need in parallel overall and how many cells I need in series overall. But even when I know how many I have in parallel and series, I can break them up into modules in different ways. So a module is just a grouping of cells, and ideally a battery pack is created simply by bolting together identical modules in some way. So that I don't have to have 10 distinct modules in an application. I want to have 10 identical modules in an application so that I can minimize the non-recurring engineering costs, in other words, the design costs. If I can design one module and use that a lot of places, that's overall cheaper than having to design 10 different modules for 10 different places. So reusable design is a really important idea. So how you make the modules is usually some combination of the two extremes that I show here. One of them is, well, suppose I have 96 cell groups in series and 3 cells in parallel, which, by the way, is the size of a Chevy Volt battery pack overall. How could I do that? Well, one extreme is to make a module, this blue shaded thing, that controls 1 cell in series and 3 in parallel. And we'll call that a parallel cell module, or PCM. And then I put 96 of these PCMs in series to make up my battery pack. The other extreme would be this one here, where I put 96 cells in series and 1 in parallel, if you will, inside a module. And then I put 3 modules in parallel. The module comprises series connected cells, so it's a series cell module, or SCM. So here I need 3 modules of 96 cells each. Here I need 96 modules of 3 cells each. And they have their pros and cons, and one of your first homework assignments actually is to investigate some of those pros and cons. Usually, in an application, you'd make a compromise. You'd have a certain number of cells in parallel, and then you'd have a certain number of cells in series, usually to keep the module voltage, again, less than 50 volts. But it's good to look at the extremes and understand the extreme cases before you actually go out and design some real thing. So we can design battery packs and battery management systems for either one of the extremes and anything in between. And you'll see battery packs referred to having configuration something like this, like 3p6s, which means that there are 3 cells in parallel and 6 cells in series. So if that was a module description, there would be 18 cells overall in that module. And I shouldn't say pack, I should say module. The module power and energy are approximately 18 times that of a single cell, although not quite in practice. It's going to be somewhat less than that because of the cells not all being identical to each other, but it's roughly that. So for a back-of-the-envelope design, you could think of it that way. When we make the battery pack, when we make the modules, you've got all of these cells in there, and we're going to need to be able to measure all of the voltages and so forth of all of the cells. And if I've got wires connected to every cell, it can just be a nightmare. There's hundreds of wires everywhere and so forth. So we need ways to control the wiring. And so cells in a module are usually welded or screwed to, affixed very firmly to some common printed circuit board, and that printed circuit board often has local battery management system electronics for voltage measurements and cell balancing, and that minimizes the nightmare of individual wires going to hundreds of cells. That's typical. That's not always the case. I've encountered one automotive battery pack recently where, in fact, there were individual wires from all of the cells to a central controller. So, but those cells were actually screwed very firmly to an electrical bus because you want to. This is for ease of connection. It's also for low resistance. You want very low added resistance connections between the cells. Before we finish this topic, I will introduce the ideas of the required functionality of a battery management system, and you'll see that there's a list numbered 1 through 5. And we will, the remaining topics in this chapter of notes will use the numbering 1 through 5 to identify how that topic is being broken out in more detail in this chapter. So we will discuss at some level all of these topics in this chapter, although we will discuss several of the topics in much more detail in the following chapters. Here's an overall picture of what it looks like in a vehicle. I've got a lot of cells, and I've drawn them wired in series, although there could be parallel wiring as well. And these cells are wired in series, and the thick line here is to indicate a high current, high power kind of wiring. So the cell wiring goes through this green block here, which has contactors in it and measurement systems in it, and then goes out here to the load. In a vehicle, that would be the power inverter that drives the motors, for example. Contactors are large relays. They open and close. They're a big switch that connect or disconnect the battery cells from the load. So generally, if the vehicle is off, the battery pack is disconnected from the load for safety reasons and also for power or energy reasons. I don't want some kind of parasitic load draining the battery pack, so I disconnect it. So contactor control and pack measurement, that's where we measure the pack voltage on both sides of the contactor. So I measure voltages here and here, and we also measure current going from the battery pack to and from the load. In the center of this, we have the battery management system. That's what we're talking about in this course. We do mention contactor control and pack measurement, but the battery management system coordinates all of those activities. And it coordinates the cooling or sometimes even heating system as well to ensure that the battery pack is kept at a proper temperature. You see this blue line here connected to the cells. That's some kind of a voltage sense line, and there may be other sensors as well. And that just indicates there's signals, not power, but there's signals coming from the cells into the battery management system. The battery management system does analysis on the values that it is able to measure, and then it informs the vehicle control computer or the load controller how much power is available, how much energy is available, what is the state of health, all kinds of things that the application may desire to know. So that's where the battery management system lives, and this yellow box here is meant to depict the battery pack enclosure. So the battery pack has cells in it, but it also has electronics in it. It has maybe the cooling system or parts of the cooling system and so forth in it. So if you open up an electric vehicle, you're going to see this big box, and it has a lot of that in it as well. Sometimes it even has a charger built in to that box. So I think I say that here. The battery management system is interconnected with the battery pack components and with the vehicle control computer, and it has functionality that we can describe as follows. So functionality element number one, we need to sense things and control things at the high voltage level. So I measure voltages of every cell, I measure current of the battery pack, I measure temperatures at multiple locations, I control these high voltage contactors. The pre-charge is an aspect of the contactor control that we will talk about. We also want to know if there's a ground fault, which is a safety concern, and we want to be able to do thermal management. All of that is under the heading of sensing and high voltage control, and we will discuss that later in this chapter under requirement 1. Requirement 2 has to do with protection. We want to protect the battery pack, if possible, against overcharge and overdischarge, against overcurrent and short circuit and extreme temperatures. There's limitations to what we're able to do, and so I will discuss mostly ways of thinking about this. I certainly don't tell you what to do about this, but there's ways of thinking about this that you would have to consider in a design. Requirement 3 has to do with interfacing with the application. There may be some range estimation if this is a vehicle application. There's certainly communications required between the application and the battery management system. There's some data recording, and there's some reporting requirements. So we'll talk about those. Topic 4 is performance management, which has to do with estimating the state of charge, how much power is available, and maintaining the cells in some kind of balance so that they're able to achieve the operational objectives of the battery pack at any point in time. And finally, diagnostics. Diagnostics has to do with being able to determine if there is abuse because the application is not following our advice, or even under normal operating conditions as the cells degrade, estimating the state of health of the cells, and sometimes the state of life. So the state of health is where am I right now, the state of life is how much more time do I have, kind of prognostic. So in this chapter, we're going to address all of these to some degree, and our focus is on some of the more basic design considerations, but still important, that would definitely have to be thought about carefully when we make a battery pack design. Later chapters are going to develop the performance management and diagnostic aspects in much more detail. That's really the focus of the course, tends to be in those two areas. So that is the high-level introduction to what a battery pack is and what a battery management system is and what it does. The next topics are going to go through these requirements and to discuss them in a little bit more detail. So we're going to start next topic on sensing and high voltage control.